Welcome to page 3, and page 3 we're going to talk about level curves. And so what the level curve is the level curves of a function f of two variables are the curves with the equation f of xy is equal to k, where k is a constant in the range of f. So basically what our k's are is our k's are basically cutting slices into whatever shape that we have. And then what we're going to do is per all those slices, we're going to project those onto a two-dimensional plane. And so that k just allows us to show the differences as we go up along the z-axis. So a level curve of f of x y is equal to k shows the graph of f has height k. The surface is steep where the level curves are close together, and it is somewhat flatter where they are farther apart. One common example of level curves occurs in topographic maps of mountainous regions. The level curves are curves of constant elevation above sea level. So I'm sure quite a few of you have seen these types of maps, and you're able to read these maps. And so again, the closer that the lines are, the steeper, like if it's a mountain, the steeper that the mountain would be. Another common example is the temperature at locations xy with longitude and latitude. Here the level curves are called isothermals and join locations with the same temperature. So, example 4, we're just going to answer these questions pretty quickly, and then and that's it. It's not going to be something it's going to take a long time. So, shown is a contour map at atmospheric pressure in North America on August 12, 2008. On the level curves called isobars, the pressure is indicated in millibars. Estimate the pressure at C, N, S, and V. So let's go ahead and do that. So we're estimating the pressure at C. So Chicago, I'll go ahead and write it out. You can just write C if you want to. Nashville, San Francisco, and then Vancouver. Alright, so I'm just going to denote what we perceive the temperatures to be in red. So in Chicago, notice the distance between the two isobars at 1012 and then 1016. And I'm just going to connect, a line right in between those two. And notice that it's closer to, 1012, but it's greater than 1012. And it looks like, it's a distance about a quarter of the way. So a quarter of the way would be 1013 for Chicago. So we're going to say 1013. Again, this is just us estimating, so I'm not going to say 1013 is perfect, but that's what it looks like. So 1013 millibars. All right, what about Nashville? Nashville looks like we're very, very close to 1012, and we look at 1008, and if I connected a line there, it looks like it's just pretty much on 1012, so we can go ahead and say Nashville is 1012 millibars. San Francisco looks like it's right in between these two isobars of 1012 and 1008, so we're going to go ahead and say that's 1010 millibars. And then if we try to Vancouver looks like it lies, so we have 1016, and it looks like it's getting bigger, because here's 1012, 1016, so then it's headed to 1020, but it looks like it's pretty far away, but we don't know really how far away, so we can say, if you wanted to say 1016, that's fine. I'm going to go ahead and say this is 1017 millibars. And that's it. So again, something that's not very difficult, just to help, get us reading contour maps. Now, let's look at, so this was A. let's look at B. At which of these locations were the winds the strongest? All right. And as we look, it looks like, where the isobars are closer together, the level curves, that's where the winds are the strongest. So looking at our picture, where are the isobars closest together? Well, the isobars are closest together, it looks like at San Francisco. So therefore, San Francisco is where the winds are going to be the strongest. So we'll say San Francisco. And I'm just going to write out why I explained it, but I'm going to write that out real quick. Because winds are stronger where isobars are closer together. All right, and that's it. I'm going to highlight that and we're done. So hopefully, that one wasn't too bad.